Hello everyone, welcome to Lesson 9 of Pre-Algebra. In our lesson today, we will introduce a new concept in number theory called least common multiple. We're going to go through a few examples on how to find it, and then go into a set of practice problems that uses it in our problem-solving process. So let's get started. So what is least common multiple? If I have a set of positive integers, least common multiple is that smallest multiple that's common to all the integers within the set. So if I have the number 4 and 6, what is the least common multiple for them? You probably are immediately thinking 4 times 6 is 24. So the number 24 is a common multiple. That is, 24 is a multiple of 4, and it is also a multiple of 6. But it is not the smallest one, so it's not the least common multiple. If we write out all the multiples of 4, what we have is 4 times 1, 4 times 2, 4 times 3, 4 times 4, 4 times 5, and 4 times 6. I'm going to stop right here. And if we write out all the multiples for number 6, what we have is 6, 12, 18, 24. So here you see 24 is a common multiple to both 4 and 6. But it is not the smallest one because here we have 12 that is also a common multiple to number 4 and 6. Now the way to go about finding the least common multiple is we first do a prime factorization on the set of numbers and then find all the prime factors for each. So if here we have 4 is equal to 2 times 2, 6 is equal to 2 times 3. So this is all the prime factors for 4 and 6. So you can see we have a common factor, 2 here. Then we have a separate 2 that belongs to the 4 and a separate 3 that belongs to the 6. In formulating the least common multiple, we need to only use the common factor once. So we first write out our 2, that's this common factor. Then we have another 2 that comes from the 4. Then we have another 3 that comes from the 6. And we're going to multiply all of them together. And that equals to 12. So this is the least common multiple. So another notation to denote least common multiple is usually written as LCM in short, and followed by the numbers that we want to find the LCM on, and that equals to 12 in our case. Let's look at one more example. What is the least common multiple for 10 and 12? So if we multiply 10 and 12 directly, that equals to 120. So this number is a multiple of 10. It is also a multiple of 12. But it is not the least common multiple because both 10 and 12 has a common factor, number 2. So if we write out the prime factors for 10, that equals to 2 times 5. And for 12, that equals to 2 times 2 times 3. So here we have a 2 that is a common factor to both numbers. And when we formulate our LCM, we only need to use this common factor once. So if we write the same shorthand notation for LCM on the numbers 10 and 12, that equals to the 2, which is a common factor, multiplied by the 5 that comes from the 10, multiplied by the 2 that comes from number 12, and then multiplied by the 3 that comes from number 12. And this whole thing equals to 60. And this is the least common multiple for 10 and 12. Now, as you recall in our last lesson, we learned Venn diagram. As a quick refresh of memory, in a Venn diagram, items are grouped in overlapping circles, and we can use it to help us visualize the relationship of items with respect to a group or groups. And in our particular case, we group the prime factors of a number into a circle. One circle for one number, and the overlapping region is where the common factors of the numbers sit. So next we're going to see how we can actually use a Venn diagram to find the least common multiple. So let's look at these same two sets of numbers again. To find the LCM for 4 and 6, we're first going to find the prime factors for each. So 4 is equal to 2 times 2, and 6 is equal to 2 times 3. So here you can see 2 is common to both. Now we're going to draw our Venn diagram. We have one circle that will group all the prime factors for number 4. Then we have another circle that will group all the prime factors for number 6. Okay, so because 2 is a common factor to both, so it will be sitting in this overlapping regions where the two circles overlap. Okay. Then we have another 2 that belongs only to number 4, so it will be sitting right here. And we have another 3 that belongs only to number 6, so the 3 will sit here. So the product of these three numbers shown in the diagram is the LCM. So if we use the shorthand notation, LCM of 4 and 6, that equals to 2 times 2 times 3, and that is 12. Now for number 10 and 12, we're using the same method. The prime factors for 10 is 2 and 5. And for 12, that equals to 2 and 2 and 3. So we're going to use another two circles, one for number 10 that will group its prime factors, and another one for number 12 that will group its prime factors. So here, the common factor is 2. So this 2 will sit in the overlapping region of the two circles. Then we have a 5 that belongs to the 10. We have another 2 that only belongs to number 12, and we have a 3 that belongs to the number 12. Okay, so the LCM of 10 and 12 equals to the product of all the numbers in the Venn diagram, and that equals to 60. In this example, we're going to find the LCM of three numbers using the Venn diagram. So as a first step, we're again going to find all the prime factors for 36, 48, and 90. Okay. So 36 equals to 2 times 2 times 3 times 3. And 48 equals to 2 times 2 times 2 times 2 times 3. And 90 equals to 2 times 3 times 3 times 5. So here is our set of prime factors for these three numbers. Okay. And next, let's draw out our Venn diagram. So we're going to have one circle that will group in all the prime factors for number 36. Then we have our second circle that will group in all the prime factors for number 48. And then we have our third circle that will group in all the prime factors for number 90. Okay. And we're going to fit all of these prime factors into their relative locations in this Venn diagram. Okay. So first, let's look for common factors that exist in all three numbers, which we have. We have a 2 here, and we also have a 3 here. So the 2 and the 3 are going to sit in the center region right here, where all three circles overlap. Next, let's look for common factors between two numbers. So let's start with 36 and 48. So for 36 and 48, we have a 2. Okay. So this 2 will sit right here where these two circles overlap. Next, let's look between 36 and 90. So for 36 and 90, we have a 3 that is common to both. So the 3 will sit in this region right here where these two circles overlap. Okay, so for the prime factors that are left, we have 2, 2, 5, nothing in common. Okay, so we're going to place the 5 in this region right here where it only belongs to the circle 90. and we're going to place 2 multiplied by 2 in this region here where it only belongs to number 48. Okay, so our LCM for these three numbers of 36, 48, and 90 is equal to the product of all the numbers in the Venn diagram. So that equals to 2 times 2 times 2 times 2 times 3 times 3 times 5. And if you multiply all of them together, you will get 720. And this is the LCM for these three numbers. Okay. So this is the end of our examples, and we're going to walk through several practice problems next, and we'll be using LCMs and GCFs to solve them in the process. So let's take a look. Let's look at our first practice problem. Integers a, b, c satisfy the following condition. What is the least possible value of LCM for a, b, and c? So we have a set of GCFs amongst these numbers. Let's use a Venn diagram to help us understand and visualize these numbers. So we have one circle that will group in all the prime factors for number A. Then we have another circle that will group in all the prime factors for number B. And we have our third circle that will group in all the prime factors for number C. Okay. Now the problem said GCF of ABC is equal to 1. So the center region where all three circles overlap will have a 1. GCF of A and B is equal to 3. So the circle A and B where they overlap will have a 3. GCF of A and C is equal to 4. So the overlapping region of A and C will have a 4. And lastly, GCF of B and C is equal to 5. So the B and C overlapping region will have a 5. So we have mapped out all the given conditions onto the Venn diagram. Now for A, B, and C, they each will have some prime factors that are unique to them. And let's denote that with capital A for A, and capital B for B, and capital C for C. So we have completed our Venn diagram. So from our Venn diagram, the LCM of all three numbers is essentially all of them multiplied together. And that equals to A multiplied by B multiplied by C multiplied by 3 multiplied by 4 multiplied by 5. Okay. Now the problem is asking what is the least possible value of LCM. So we want to make this as small as possible. That means A, B, and C must all equal to 1. So this thing equal to 1 so that it's smallest number possible. And this leaves us LCM is equal to 3 times 4 times 5. And that equals to 60, which is our answer. Let's take a look at this next problem. A church rings its bell every 15 minutes, a school rings its bell every 20 minutes, and a daycare rings its bell every 25 minutes. If they all ring their bells at noon on the same day, at what time would they next ring their bells together? Now let's think about this problem. So for the church, it rings its bell every 15 minutes. So the first time it rings its bell is 15 past noon, then 30 past noon, then 45 past noon, and then 60 past noon, and then so on and so forth. Now for the school, it rings its bell every 20 minutes. So the first time it rings its bell is 20 past noon, then 40, then 60, then 80, and then so on and so forth. Now for the daycare, it rings its bell every 25 minutes. So we have first time rings its bell at 25 past noon, then 50, then 75, then 100, and then similarly so on and so forth. Okay? So you'll notice in each sequence, the numbers are multiple of the first number in the sequence. So 30, 45, 60, these are multiples of 15. And similarly, these are multiples of 20 and these are multiples of 25. Okay? So as these sequences goes on, the first occurrence of a number that appears in all three will be the common multiple to 15, 20, and 25. And because it is the first occurrence, it is also the least common multiple. So we want to find the LCM of 15, 20, and 25. Okay. So 15 is equal to 3 times 5. 20 is equal to 2 times 2 times 5. 25 is equal to 5 times 5. Now to find the LCM, we first find all the common factors and write them out once, which we have a 5 here, and we have no more common factors left. So we multiply the rest of them together. Okay. So 5 times 2 is 10. 2 times 5 is another 10 multiplied by 3. So we have 3 times 10 times 10, which is 300. So this means in each sequence, they will eventually reach the number 300. Okay. And this 300 is also the time interval they will next ring their bells together. So 300 minutes is equal to 5 hours because there are 60 minutes within an hour. So 300 divided by 60 is equal to 5. And if we start at noon, 5 hours from noon is 5 p.m. Okay. So 5 p.m. is the time that they will next ring their bells together. Let's look at this problem. Alex counted to 2,400 by sixes, beginning with 6. Mike counted to 2,400 by fours, starting with 4. How many of the numbers counted by Alex were also counted by Mike? Let's first write out the numbers that are counted by Alex and Mike in sequences. So for Alex, he starts counting as 6 and increments by 6. So his numbers are 6, 12, 18, 24, 30, so on and so forth, until he reaches 2,400. Now for Mike, he starts counting at 4 and increments by 4. So his numbers are 4, 8, 12, 16, 20, 24, until he also reaches 2,400. Okay. So again, the numbers in each sequence are multiples of the first number in their sequence, okay, which is 6 and 4. And the numbers that occur in both sequences are common multiples of 4 and 6. If we find the first one, which is the LCM, then we can find all of the rest of the common multiples. And these common multiples are numbers counted by both Alex and Mike. So the LCM of 6 and 4, that equals to 6 is equal to 2 times 3, and 4 equals to 2 times 2. So 2 is a common factor in both, so we write that out once, and then we write in rest of the prime factors, okay? And this equals to 12. So LCM is equal to 12, and LCM is our first common multiple. So the next common multiple will be 12 times 2, 24. The next one will be 12 times 3, 36, until 2,400. So this is the set of numbers that will be counted by both Alex and Mike. We start with the first equal number 12, count to 2,400, and with an increment of 12. And how many numbers are in this sequence? That is 2,400 divided by 12. And this equals to 200. So there are a total of 200 numbers will be both counted by Alex and Mike. Let's look at another problem. The people in the party try to form teams with the same number of people on each team. But when they try to split up into teams of 2, 3, 5, or 7, exactly one person was left without a team. What is the smallest number of people greater than 1 could have been at the party? Okay. So this is an interesting problem. No matter how they split the team, there will always be one person that's left out without a team. Let's assume that we temporarily invite the person to be outside of the room and find the total number of people that is inside the room. Okay? So if we split up the teams into 2 people per team, For one team, we have 2 people. 2 team, we have 4 people, and then so on and so forth. Now, if we split up the team into 3 people per team, then for one team, we have 3 people, 2 teams, 6 people, 9, 12, 15, and so on and so forth. And if we split up into 5 people per team, we have 5 people for one team, 10 people for 2 teams, 15 for 3, and then 20 and 25, and so on and so forth. And for 7, we have 7 for one team, 14 for 2 teams, 21, 28, 35, and so on and so forth. Okay? So no matter how they split the team, the total number of people inside the room will always remain the same. That means each of this sequence of numbers will eventually reach the same number. And that number is the least common multiple of 2, 3, 5, and 7. So we want to find the LCM of 2, 3, 5, and 7. Okay? Now these 4 numbers are all prime numbers. So the LCM for them is simply 2 times 3 times 5 times 7. Okay? And that equals to 2 times 5 is 10, 3 times 7 is 21, 21 times 10 is 210. So there are a total of 210 people inside the room. Now remember, there's one person that's still outside of the room. And if we bring him back into the room, it becomes 210 plus 1, which is total of 211 people at the party. And because this number comes from the LCM, so it is the smallest number of people that can be at the party. Let's take a look at this problem. The least common multiple of 12, 15, 20, and k is 420. What is the least possible value of the positive integer k? Okay. So the question is asking the LCM of 12, 15, 20, and k is equal to 420. What is the k right here? Let's first dissect how this 420 came about by writing out all the prime factors for the given numbers. So for 12, that equals 2. 2 times 2 times 3. 15 equals to 3 times 5. 20 equals to 2 times 2 times 5. And then we have k. Okay. So the LCM, if we use our method, we first find the common factors. So we have a 2 here that is common. So we have 1, 2, and we have another 2 here that is also common. And then we have a 3 that is common, and we have a 5 that is common. And we're left with a k. So all that multiplied together equals to 420. Now this right here gives me 60. So 60 multiplied by k is 420. And that leaves me with k is equal to the number 7. Let's take a look at our last practice problem. Suppose a and b are positive integers with a greater than b, and the LCM of a and b is equal to 462, and the GCFs between them is 33. Find the largest prime factor of a that is not a prime factor of b. Okay. So there are a handful of conditions and constraints in this problem. Let's first straighten them out. Okay. So the problem said there are 2 integers a and b where a is greater than b. And the LCM between A and B is equal to 462. And the GCF between A and B is equal to 33. And we want to find the largest prime factor in A that's not in B. So as the first step, we must find all the prime factors of A and B. Okay? And how to do that? So usually when we have both LCM and GCFs, Venn diagram can help us sort through the relationships of the prime factors for these numbers. So let's first draw out our Venn diagram. We have one circle that will group in all the prime factors for A. Then we have another circle that will group in all the prime factors for B. Okay. The problem says GCF between A and B is 33, so the 33 will sit in the center region where the two circles overlap. Okay. Now A will have some prime factors that's only unique to A, and let's denote that with M. And similarly, B will also have some prime factors that's only unique to B, and let's denote that with N. So from the Venn diagram, the LCM is equal to M times N times 33. And we know that also equals to 462. So 462 is equal to M times N times 33. Okay? And from here, we can derive that M times N is equal to 462 divided by 33. And that equals to 14. And if we factor out 14, that equals to 2 times 7. So the M and N can be 2 and 7 or vice versa. Because the problem says A must be greater than B. So that means M must be equal to 7 and M must be equal to 2. So that A will be greater than B. Now from the Venn diagram, if we just look at circle A is equal to M times 33, which is 7 times 33. And if we factor out 33, that equals to 7 times 3 times 11. And B similarly equals to N times 33, which is 2 times 33. And that equals to 2 times 3 times 11. So here we found all of the prime factors for A and B. The largest prime factor in A is 11, but that cannot be our answer because 11 also is a prime factor in B. So the largest prime factor in A that is not in B is number 7, and this is our final answer. So this concludes our topic today on least common multiple. Feel free to review the example problems and practice sets. We'll see you next time.